Well, hello everyone, and welcome back to Adrian's Digital Basement. On today's video, we're going to be taking a look and trying to repair this leading edge XT computer here. Last time I tried this computer out, it had some kind of a fault. If I recall, it was with the video circuitry. So in this video, I want to try to fix it. So without further ado, let's get right to it. Before we get started with the repair, just a little bit of housekeeping. I am currently getting over having had COVID-19, and unfortunately I'm not really back to, full speed. I still have quite a bit of congestion, so you might hear that in my voice, but even worse, I'm still sort of struggling with, lower lung capacity, it feels like. In fact, it was funny because earlier this morning I was at my doctor's office, one of my doctors, and I parked on the 3rd level, and I always take the stairs back up to my car when I was leaving. And I got to my car and I sat down just 3 flights of stairs and I was completely out of breath. That is not normal for me. I'm not like the healthiest, most exercisey person in the world, but I do stay pretty physically active, out and about, riding my bike, stuff like that. And I couldn't believe that taking 3 flights of stairs totally knocked me out. So hopefully today's video is going to be a little bit easier on my brain because I'm not fully back to normal yet. So anyways, enough of that backstory. Let's take a look at the leading edge here. The leading edge, I'm pretty sure this is a Model D. I think there were 2 versions of this, a Model D, which is made by Daewoo, and a Model M. The blue logo, I don't know what that means. I think I've seen some that have sort of a white sticker on there. But either way, this thing is just a standard IBM PC XT. I'm not even sure this is turbo. It might just be 4.77 megahertz. It has I think this is a standard disk drive that was on this thing. It's just a little flip up style, and you can actually slide that thing to the left, and then it actually locks the disk in there. A little bit of an unusual feature. Keyboard port on the front, reset button, power switch, a good amount of yellowing on the front. The rest of the case is metal, so it's painted and doesn't have any yellowing, just has a few little scratches and stuff. On the back of the machine, not a whole lot to report. There are 4 expansion slots, none of them are populated. There is a color and monochrome video connector right there with a toggle switch to go between them, so you have both types of video on this machine, and you have a built-in parallel and serial port. I'm pretty sure internally this thing has a built-in floppy drive controller, so the fact that it has no expansion cards installed doesn't mean that it's not going to work and is not a usable machine. I like the fact that the pass-through power connector is actually just a standard US style plug, so you don't even need to use one of these IEC reverse gender type connectors. You can just plug your monitor directly into this thing, and when you flip the power switch on the front of this thing, it turns on whatever is connected to this connector. With the badge there, we have a leading edge model number DC2011. I don't even know, to be honest, if a Model M, which I swear I thought I had on the channel at some point, Model M being made by Mitsubishi, so Japanese made, versus Daewoo, so made in Korea. They're both XTs from my recollection, but I'm pretty sure that this Model D is the most common of the 2 variants, and if you had a leading edge when you were growing up, it was probably one of these Model Ds. I definitely have a video on one of these Model Ds that I made in the past. It was a PT Archeology video. I'll link to that in the description below, so I won't really talk too much about the features and stuff of this in this video. We just want to get to the repair. Now, what's wrong with this thing exactly? Let me grab a monitor and we can see exactly what's wrong with this thing. Change of plan, decided just to take the cover off this thing. We'll take a look inside, we'll hook it up to the RGB to HDMI. That's easier for capturing than trying to record what's off a CRT. Not much to report inside, just a standard full-size motherboard. It goes from, this side of the case all the way over to this edge. You can see there's the Daewoo name there that tell you this is a Model D for sure. One thing to consider with these things, you got to make sure you take out the clock battery. These things have a leaky NiCad type battery for the clock calendar. I've taken that out at some point in the past. The problem with this machine has nothing to do with any possible damage over here. You can kind of tell if we zoom in there that there was basically minimal damage of any kind. There's a little bit of dust and stuff over here, but basically that battery barely leaked at all, so we have no green crusties that could have affected these ICs over here. This is the standard clock chip on this machine. It is not in a socket, unfortunately, but you could desolder this theoretically, and then you could install something like a Dallas clock chip like I recently did on the Plexus P20. That would have a self-contained battery, and that way you wouldn't have to worry about even replacing this thing with something else that could leak in the future. As I mentioned, the floppy drive controller is built into the motherboard. It connects right here next to the power connector. This machine has 640K of RAM. It's sort of partially obscured by the floppy drive here. Has 128K installed on the motherboard, very skimpy, but these chips right here are 64K times 8. There's 8 or 9 of these. And then we have an additional 512K that someone has installed. Probably there are two different configurations you could have, 256K or 640K, which is what we have right here. Now, I had done a little bit of testing on this machine in the past, and I did not make a video about it. I was just seeing if it worked or not, and it didn't. And I left myself a little note on the inside here, and I said, character generator is good. I dumped it. Now, that's an EPROM. Now, I obviously took that out of this machine just to check to make sure it was still working properly, because I wrote the CGA text mode bad. So whenever you go into text mode on this thing, you get garbled text. And that's the problem we're going to be trying to fix. Let's hook this up to RGB HDMI so we can see what that looks like. Now, one of the problems that we're going to run into with this machine is that there are no schematics for this whatsoever. So we're going to have to try to use logical thinking to try to figure out which chip is bad on this thing, because there's a whole ton of ICs on here, but we don't want to go and swapping out everything. We want to try to get to the bottom of exactly which chip is bad, and we'll just do we'll use our eyes and our senses to figure out what the problem is and where the issue might lie. So for the RGB to HDMI, I'm just going to select the standard CGA profile. I don't know which one. I'll just try this new one here. Hopefully that'll work. I have power connected, the RGB to HDMI connected, plus the XT IDE installed. I plugged in an XT keyboard here, and let's power this thing on. I may have that switch set wrong. No, I think we're in the right mode, but what we're seeing here is the problem that I'm talking about. You can see the text is readable, but there's definitely something wrong with it. And this is why I thought there was a character generator problem, because that could cause issues like this. But since the character generator for CGA type cards, including what's on the motherboard here, is a standard EPROM, you can put it into something like a TL866. Just checking, okay, 640K, that works. Now it should be booting DOS. When you read out the contents of a character ROM, you can actually look at it as a binary representation and see every single bit that makes up a character. Because remember, it's just a 0 or 1 that makes up the characters, and you have rows and columns of these bits that form every single character. And when I looked at what I had dumped out of the EPROM, it all looked good. So I knew that the chip itself was working and had correct data in it. It wasn't corrupted. So this problem that we're seeing on screen here has nothing to do with the character ROM. There's something going on the motherboard. Okay, so I just ran check it because we're going to look at the character map, and right away we can see as one of the issues appears there seems to be a missing row entirely. So you see in the red tick mark there, it should be solid. There should not be any gaps between the characters, and the same goes for the check it itself. That should just be all solid without any gaps. We're going to do a video test here with the text mode, and we can see here that 40 column mode is affected in exactly the same way as 80 columns. And since the characters are larger, it allows us to more easily see what's actually screwed up. Let's take a look at this checkerboard character. This character should just be a continual set of dots in an alternating pattern across the entire character cell. And you can see one of the issues is we have an entire column of pixels that are missing altogether. But then we have two that are repeating here. But the funny thing is, take a look at this symbol, or this one here. It does not have the missing column like the one above it. That's sort of strange. And then the next thing that's funny is this column here, it doesn't seem right either, because it should have two pixels, one there and one there, and it's missing one. It also appears that we're missing an entire column right here as well. So this white line should be solid, and it's not. So I think on the left side of this checkerboard character, we should have another column of pixels that are missing altogether. Now that makes these characters look screwed up. So the Q, this is a Q, it should have pixels here, it should have pixels here as well, and then it looks like we might have a missing column as well, although this has this weird duplicate thing going on. So something definitely strange that's going on. And this is actually why I suspected the character ROM was the problem, because this type of issue could well happen with a bad character ROM. All right, so we know that there's something definitely going on with the columns of pixels in the text modes, and it affects both 40 columns and 80 column mode. What we need to do now is check the graphics modes to see if those are also screwed up. So back in the main menu here, we just go to graphics. Now graphics mode is working. Now you can ignore the little bit of shimmering we have going on. I'm just gonna try to correct that by doing the auto calibration. That is just a timing thing between the RGB to HDMI and the CGA adapter. All right, so there we go, that looks perfect now. Now we're in a graphics mode right here. That means there's no text being displayed in the normal text, the way text is displayed. The way the graphics are rendered is different than the way the text is rendered. The graphics mode loads the pixel data right out of the video memory. There's some video memory on the motherboard to display this. And it's actually serializing what's in that RAM and displaying that to screen. That's different than text mode, because what text mode does is the characters that you want to display are stored in video memory, but not the actual structure of it, just the actual value of the character. And then what happens is when it goes to display your text screen is it says, oh, okay, first character that I want to show is an A. And then it uses some special circuitry to read the character set out of the ROM, and it does that in real time. So it actually looks up using address lines, the A character in the ROM, the character ROM, and then it serializes that and then displays the first line of pixels. It goes through and does all the other characters and then the next line and so on and so forth. So the circuitry that's involved is different. So the rasterization of the graphics is working fine, and let's just go through these different modes here. There's there's 640 by 200. Obviously that's working perfectly. CGA doesn't really have that many modes. We have some color modes though. Those are working great as well. All right, so let's think about the problems we're seeing. Text mode is missing entire rows. Now what we can do is we can eliminate a whole bunch of stuff that we know is not a problem. The video memory working perfectly. If there were problems with the video memory, we would see issues in the graphics mode. There would be corruption or other types of issues. In addition, if the video memory was the fault in text mode, we wouldn't get messed up characters. We would just have the wrong character. So instead of like a screen that's blank with, A, B, C or whatever the alphabet on there, you might have a bunch of random characters mixed in instead of just a blank background. And, instead of A, B, C, you might have other characters. So the problem has nothing to do with the video memory. We can ignore that entire section of the card. All the bus transceivers that talk from the ISA bus. Now this is a CGA card, but you can imagine that on this motherboard it works similar. The CGA or the video circuitry is probably isolated, and there are bus transceivers that allow it to communicate with the CPU. That's working fine, so we can totally ignore all of that stuff. When it comes to the video output circuitry itself, what generates the CGA signal, obviously we don't have any problems there because again, graphics mode working perfectly, all the color modes are working perfectly. The issue we have with this machine exists from the character ROM to the video output circuitry. Whatever goes on in between there, that's where the issue is. So let's go to the schematics and find the character generator and then see the path from the character ROM all the way through to the video output jack. IBM actually published the original schematics for the IBM CGA card, so that's pretty handy. It's really nice they've put all those schematics out. There's a recreation of it though here on this GitHub repo, and this just makes it a little bit easier to follow because the IBM one, there's a whole bunch of pages you got to keep scrolling around. It's just nicer to see it all together here on one page. Okay, so here taking a look at these schematics, there is the character generator. It's an MK36000. This is on the actual CGA card. On this machine, it's an EPROM. On the input side, we have a bunch of address lines. Now on the original CGA card, this ROM actually contains two different fonts, the skinny font and the regular font. And I showed that in my CGA hacking video. If we put a jumper on one of these address lines here, I think it's this address line 11, you can select between these two fonts. On this computer, it's probably similar because this thing supports a monochrome mode, which has a higher resolution font versus the CGA mode. So it's probably a similar situation where if one address line is set low, then you're getting CGA font, and in the other one you're getting the MDA font. So when you look at the address lines, which obviously are used to select which character is being displayed, you'll notice that the first three lines, A0 through A2, are connected to these RA0, 1, and 2 lines. And then everything else is connected to the CC0 through 7. Well, remember that IBM PCs have a character set of 256 characters, which is made up of 8 bits. Now, when you look at A3 through A10, those lines select which character is being displayed. Now, when you think about a character glyph that is used in a pixel-based display like this, there are rows and columns that make up the character. And on CGA, a character is made up of 8 by 8 pixels. When you're displaying characters to screen, say you're displaying 40 columns across, what you have to do is you have to first select the character you're going to display, like the letter A. You would select that with those upper address lines, those 8 address lines. You're going to pick the character for A. Then what you do is, using those first 3 address lines, you're going to select the top row of pixels for that glyph. And with those address lines selected, the EPROM is going to output on its data lines that first row of pixels. What the circuitry does is it takes those and it turns them into a parallel 8 lines, and it serializes it into 8 pixels, and it draws those pixels at the same speed as the scanning electron beam on your monitor. And then what happens is the CRT controller, that's the 6845, selects the next character, and that is happening with those upper address lines, so say the letter B, and then it's still selected with the first line of pixels, and it serializes that, displays it on your screen, and then it goes through all the letters and does it over and again, and then it goes through all the rest of the letters on that line, and then it has to go down to the 3rd row of pixels, and then the 4th, 5th, 6th, 7th, and 8th, and then you have the entire character formed on your screen. Well, what we can see happening here is we know there is no problem with the selection of what row of pixels is being drawn. And that's because when we look at the glyph on the screen, we can see that, there's all eight rows of pixels are being drawn. The issues are in the columns. And when we look at the schematics, the 8 data lines that are coming out of the EPROM are actually the 8 columns of pixels. And you can see that those 8 columns, those 8 data lines, they make their way into the 74LS166, which we can just make the assumption, I haven't looked up that part number, but that is obviously a parallel to serial shift register. We have an input here of the 8 lines in parallel, and we have an output of something called character generator dots, and dots mean pixels. We have a few other inputs in here, like a dot clock input. That's to make sure that the output of this chip is perfectly synchronized to the scanning of the electron beam. We have a clear pin, and I don't know what SL does. Maybe that's like an enable pin. Now let's find out where this character dot signal goes on here. Here's one spot it goes. The nice thing about this schematic is it's searchable. This goes into that gate there, and it outputs alpha dots. And there's various things that also go into these gates, like blink and cursor stuff. And let's look for alpha dots here. Looks like alpha dots comes in here, goes through some more gates. And let's see where this comes out. Mux comes out of mux output. Well, OBS just completely crashed, and so did Chrome here, the Chrome tab. So hopefully that didn't corrupt the video too bad. Let's go back to the PDF. Yeah, this is what happened. I got this little unhappy face here in Chrome, and then OBS just went poof and it was gone. So the MUX A output of that chain we were looking at goes into this 74153. And let's see where this goes. This makes its way right here to this 74S174, and then the RGBI output. So I think what's happening is the MUX here is like mixed with color information that's coming out of a different part of the circuitry. We know there's no problem with the color circuitry because the color's working perfectly, even in text mode. That's good as well. So this is mixing like border stuff and color things with these chips, and then that generates the video output. So the problem that we're having absolutely has to exist in that chain that we just looked at. And we can ignore all that stuff at the end, and that's because we know that stuff is working because the color is working, the graphics are working, that all goes through those chips near the end. The problem has to exist either with the character ROM itself, because say one of these lines were stuck or not working, well, that would create those columns where we have gaps and stuff, or the 74LS166 is what takes the input from the character generator, converts that into the dots, serialized dots. Or it is theoretically possible that we have problems here in these gates. Although that seems highly unlikely to me, because if there was a problem, for instance, with this gate here, 74LS08, say this pin 13 weren't working properly, then we would have no text at all. We might still have like cursors and we might still have color, but we wouldn't have text. Now keep in mind, of course, we're looking at the CGA card schematics. This may be different on this computer, but I'm going to make a wager that the circuitry that's on this computer is going to be similar to what's happening on the CGA card here. So let me get this computer apart and let me take this power supply out of here because I think the circuitry is underneath it. And let's see what we can see when it comes to these types of chips on this motherboard. Computer's been disassembled. It's really kind of annoying to work on because I need the power supply to be able to power up the computer, but it has the shortest little power cord here. I'm not sure if this is a standard pinout either, so I could just use any old power supply. So for now, I'm just gonna use this off to the side like here. And the video circuitry that we're looking at is down here in this area. And I'll get my little pointy stick here so we can kind of point at various things. So we have the character generator right here. It even says char on it there. So that makes it very obvious. We have the video memory right here. Two of these chips is actually 16 kilobytes. So this thing actually has 64K of RAM, which is quite a bit more than CGA. Now it might be because in monochrome mode, it has Hercules compatibility, which requires 64K. But it also could be that this thing supports like a Plantronics type video mode or some other 320 by 240 16 color mode like Plantronics or EGA or Tandy or whatever. I'm not quite sure. There's the 6845. That chip is in, must have had a sticker on top of it that peeled off. It looks like it's a Motorola part. There is a 74LS166 right there. So I wouldn't be surprised if we take a look at the data lines, which are these pins here and there, that those go over to this chip. Let's take a look. Okay, we'll start with this random pin right here. There we go. And the next one up, there we go. So on and so forth. Yep, okay, so it's exactly as the IBM CGA card is, where the output of the character ROM just goes right into the 74-166 here, and then it is turned from parallel bits to serial. So what I'm gonna do is power up this machine. It is working. I have a mouse pad here, so it won't short to the motherboard at all. Oh, I gotta plug a keyboard in. And there we go. And I hit F1 to boot up. And the reason why I want to do that is I'm just gonna switch this thing into 40 column mode once this boots into DOS. And then we'll be able to probe around on the output of the character ROM, see what we see. So you just say mode CO40, and that's for color 40 column text mode. Let's put a bunch of characters on the screen. In fact, do DIR here. That way we have something to look at when we're probing around on the outputs of the character ROM. Okay, so let's use the Zoe here, and this is what we're gonna use just for taking a look at the output of this chip here. This is the pinout of the chip we're dealing with here. So Q0, pin 11, all the way through pin 19 there, Q7. So those are the output data lines. We need to see activity on all of those to ensure that the lack of those columns is not coming from this chip and is instead coming from the 74LS166 right here. So this is data line 0, pin 11, looks good. There is data line 1, data line 2, data line 3 looks good, 4, 5, 6, and 7. They all look good. Now, when you look at these, you'll notice that like 7 doesn't seem to have that much activity on here. And I think the reason why is because there's just not a lot of pixels always in that 7th row. If you think about letter like I, it doesn't have anything in here. Or a bunch of other characters mainly have pixels around the middle. So 7 and 0 are probably going to be the least busy. And yep, that's 0, sort of similar. Different, but similar. But what we are getting is we're getting signals on every single pin on the output of this chip. That kind of tells us there's nothing wrong with this EPROM. And the problem has to lie in this chip right here. It has to. That's the only thing that makes sense. Now there's actually another test we can do. I'm gonna power the computer off here, and I'm gonna actually remove this from the motherboard altogether. And then what we can do is we can actually short the output lines or bring them up to 5 volts or bring them down to ground. And we can look on the video signal to see what we see on the text mode. Now on the schematics for the CGA card, there were no pull-up resistors from the outputs of this going into that shift register. It essentially is gonna leave those inputs floating. So when we turn the computer on now, I'm not 100% sure we're gonna get maybe a solid black screen, maybe a solid white screen. But theoretically, if we get a solid white screen, we should have missing rows because we know there's something wrong with the inputs on this. But then what I can do is I can take a resistor and go between the 5 volts on the EPROM socket and the data lines. And in a normal situation, if we're getting an all black screen, then we should start seeing columns, maybe one at a time. Or if we have an all white screen, then I would use a resistor to bring it down to ground. Then we should start seeing columns of black pixels. But either way, let's turn this on and let's see what we see. So there we go. This is showing right here that there's a problem. I think what we should be seeing is a solid white screen right now. the floating inputs to the 74166 with the chip removed should just show all white. Now, the border is going to be black, and there's a cursor there that is flashing, and that's normal. But let me grab a resistor and start pulling the output lines down to ground, and that should start turning off these columns. Okay, so I just grabbed a random resistor here, and I stuck it into the ground pin. And let's ground. Okay, yep, you see that? I'm grounding one of the pins. And it makes like a bunch of columns turn off. Has this computer booted up? No, I think it hasn't because it's sitting there with an F1 prom. Let me boot in and switch to 40 column mode. Okay, I think we're good. Mode CO40. There we go. Now we're in 40 column mode, a lot easier to see. Okay, there we go. I'm grounding one of the data lines right now. I am grounding data line 4. And now I'm grounding data line 3. And here is data line 2. And here's data line 5. Data line 6 has no effect. It just causes a little bit of static. So there's one of our bad inputs on the 74 LS 166 right there. And then this is 7, that's working. And then here's data line 2, so that's working. And then we have data line 1, that does nothing at all. And then there's data line 0, and that works. But data line 1 has no effect at all. And what was it, number 6 also? No effect. So without a doubt, that tells us, move this over a little bit, without a doubt, that is telling us that this chip right here, the 74 166, is freaking bad. And we know for sure that this EEPROM is not the problem. 100% for sure, it is not this chip. It is this chip on the motherboard. So what's kind of cool here, I think it's kind of cool at least, is I was able to show you don't even need to have an oscilloscope to test this particular symptom. I was able to use a resistor and know for sure that it's the chip on the motherboard that's the issue, and it's not this EEPROM. And yeah, so now I just need to desolder that chip, socket it, and swap it out. Okay, so the bad chip is out. Here it is right here. Quite easy to desolder, no issues on this motherboard. I went into my spare parts and I found 3 replacement chips, all untested, but hopefully one of these works. While I was at it, I also installed the 2 pins for the battery that I cut out of this thing, so it'd be easy to restore the clock to a working condition using an external CR2032. The EEPROM's reinstalled, but the 166 is not back in the motherboard. Let's just try it to see what it looks like without this chip installed. My assumption is we'll just have a solid white screen now in the text area. Let's turn this on. All right, there we go. Yep, just like I thought, solid white screen. So the border area is still working. The flashing cursor we can't see because it flashes white on the white screen. And that's a good sign. If we saw columns still, then we would somehow know that the problem lay beyond this chip, but I don't think that's possible. Everything that lay beyond the 166 on the schematics were just regular gates, and you wouldn't get like columns with that. You would have lots of interference or no picture whatsoever. All right, let's try this 1982 Mitsubishi chip here, 74LS 166P. There it is, installed in the board. Let's give it a test. Here we go, moment of truth. 3, 2, 1, power on. There we go, it looks good. It looks freaking good. Perfect, absolutely perfect. We'll go to mode CO40. Oops, DUR does not work. There it is, looks good. There we can see there are no lines anymore in the tick mark or in the white area. All right, and as you can see, everything looks absolutely perfect in here. The text looks good. You can see the checkerboard character there. It doesn't have any missing characters. It's just, everything looks super duper good. Yep, this is as expected. This is exactly how it should look. Okay, the computer is back together. I have the Commodore 1084 monitor hooked up to it. CGA compatible. It's one of the reasons why I absolutely love these monitors. The monitor is plugged into the power on the back, that extra plug there. Let's turn this on. Let's see how this all looks. There we go, it looks really good. Text is looking absolutely perfect on there. Glorious CGA color, looks vibrant and sharp. I do notice that this particular card that's in here, I don't think it suffers from snow. I mean, the card, I called it a card. The CGA circuitry in here, it does flash the screen, so it turns it off during scrolling, which is that snow mitigation that is absolutely not required. If you want to know more about the whole CGA snow situation, I made a video on the second channel, which I'll link below, and I talked about the snow and how to bypass it and hardware hacking and stuff like that. Running Jim Leonard's CGA compatibility suite here, we can pretty much say that the compatibility of this thing is going to be 100%. There we go, we got raster bars looking good. Maybe they're slightly jittery, if anything, but they look pretty good. And then of course this supports the row reprogramming, which gives us these pseudo high color, high resolution modes that are only possible on fully CGA compatible cards. And the final test is, let's just try Planet X3 using the Plantronics Mode 6 here. Let's see if this thing actually does support the extra colors. No, it does not. So we only got the 4-color CGA mode, and that's what happens if you're trying to run the Plantronics mode on a card that's not compatible. That's not to say that this doesn't support some other 16-color mode, I just don't know what it is. And if you happen to know that this computer does support 16 colors and 320 by 200, because it does have the right 64K of DRAM to allow that to be possible, then definitely put a comment down below. Anyhow, this computer is fully operational and is fully fixed. The only fault with it was this 74LS166, and we were able to figure out exactly which chip was bad by using some logical reasoning, using our senses to see the visual problem, and then also checking the schematics on the IBM CGA card, just making the assumption that it was going to be similar to the circuitry that was on this motherboard since, well, back in the 80s, that was pretty much all that was going on. Companies were just taking the IBM stuff and just shoving it onto copycat cards or motherboards and things like that. So that's what was going on here. If you enjoyed this video, I'd appreciate a thumbs up. If you didn't, you know what to do. Sorry I haven't gotten back to more complex topics like the Plexus P20. I'm pointing to it right here. My brain is just not quite ready for thinking about really complicated videos yet, hence the need for me to do more simple repair videos like this one. If you have any thoughts about the video, comment down below. Subscribe if you haven't already. Huge thanks to my patrons. Their names are scrolling off the side of the screen. And I think that is going to be that. So yeah, stay healthy, stay safe, and I'll see you next time. Bye-bye.